Thanks for having me. Um, yeah, so today we'll talk about scaling data constraint language models. The paper is on arXiv, and this was a joint project with lots of amazing people. And we'll start by looking at scaling language models more generally, a quick background on what is scaling, why are we scaling these models, and how are we doing it. And then in the second part, we'll go into data constraint scaling. Specifically, can we use repeated data to scale them further? And mixing modalities, specifically code and natural language, and revising existing filtering strategies. And yeah, during the talk, just feel free to jump in with questions or thoughts. Don't hesitate. All right. So what is scaling? It really comes down to two ingredients. One is model size, as measured in number of parameters, and the second one is training data, as measured in number of tokens. And together, they make up the training compute, as measured in flops, floating point operations. And that's essentially the proxy for the scale of our model. And they relate to each other with some constant A, but generally it's just parameters multiplied by tokens. And over the past few years, we've seen a bunch of models that have had various scales. So we had BERT in 2018 with 100 million parameters, 250 billion training tokens, and then the corresponding flops for that. And then 2 years later, we had GPT-3 with a much bigger scale, so roughly 1,000 times the compute of BERT base. And they scaled up both model size and training data. And then recently, another 2 years later, we had Palm, which was even bigger, roughly 10x GPT-3. And again, they scaled up the number of parameters and the training tokens. And so why have we kept scaling these models over the past few years? And the reason really is that as we scale these models across these axes, we see continuous improvements as measured here in lower test loss. So that's our performance proxy. And as we scale up model size or training data or compute, which are on the x-axis, then we see continuous improvements in test loss. And here the x-axis is in log, and then the y-axis is test loss, and over several orders of magnitude, so several orders of magnitude of model size, training data, and compute, we see continuous improvements in test loss. And in fact, this relationship relates to each other in a power law relationship. So the test loss improves as a power law of those axes. And this was shown by prior work. And now that we know that, okay, scaling is very beneficial, and we keep getting better performance, we have to ask ourselves, how do we scale best? So given that we have these two axes, model size and training data, how do we use our existing compute in order to make the most use out of it? And the current consensus is that we should scale them equally. So here we have the number of parameters on the y-axis, and then the training data on the x-axis, again, both in log. And the gray line demonstrates sort of the optimal scaling. And Chinchilla, which is the kind of the blue star, outperforms all the other models because it lies directly on this optimal gray line. And the other ones, they over allocated to parameters a lot, and so they perform worse than Chinchilla. And so the conclusion is, okay, we have to scale these models equally. So we take a given compute and we equally scale up model size and training data as we get more compute. All right, and in that same paper, they also put forth a predictive formula for estimating the loss given the number of parameters and the training data and a bunch of learned constants. So they relate to each other in this relationship. We have A, B, alpha, beta, and E, which are all just learned constants, and then our number of parameters N and the training data D. And they find that when you fit this formula on lots of training runs, then alpha is roughly equal to beta. And this corresponds to this equal scaling of N and D. Because if we now increase N, then if we increase N, then L goes down, but we quickly hit diminishing returns, and we have to increase D by the same amount to get the most out of our compute. So we kind of scale up N and D in equal proportions to get the lowest loss. All right, and so we have these two ingredients, number of parameters and training data. And while number of parameters is really just changing a tiny part in your code, you might have to make sure you have enough machines, but at the end of the day, you have to change something in your code. Data has to be acquired externally, and it is constrained. So here we have a plot from prior work where they show that given this current trend that we saw of larger and larger models, it seems like we're running out of data, out of high quality language data in 2024 or 2025, as measured on the x-axis. And when we talk about high quality language data, we refer to stuff like papers. So we have roughly 1 trillion tokens of papers on the internet. So that's archive, bioarchive, and so on. And then we have books, where there's roughly 1.6 trillion tokens. So together, that's like 2.6. And that's not that much, actually. If we look back at this plot, then the chinchilla model was roughly in that regime. So we're already out of papers and books, assuming that they had access to all papers and books. And then we have a bit more high quality data from sources like Wikipedia and so on, but there's really not that much. And we're kind of running out of it. We also have code. So there's roughly 14 trillion tokens of code on GitHub. And I think that's the main source for code data. But it's not super clear whether that's whether all of that is high quality. So probably it's a bit less, actually. And then finally, there's low resource languages, which are already hardcore data constrained. So for example, recently I was working on this, on training a large language model for Finnish. And they have like 6 million speakers. So it's not a super low resource language. It's actually kind of big. It's a quite big country. But all we were able to get was 38 billion tokens, even though we partnered with a bunch of private companies that gave us access. We had partnerships with libraries that gave us their data, and that was all we were able to get. So 38 billion tokens, that's not a lot. So it was pretty hard to train a large model for that language. All right, so now that we know that we're data constrained, we'll go to the second part and look at how we can solve those data constraints. Yeah, feel free to jump in if there are any questions at this point or anything that's unclear. Okay, cool. Then let's look at data constraint scaling. So the consensus prior to this work was that repeating data is harmful. So one easy remedy for the data constraints is just you just repeat those 1 trillion tokens of papers. You just keep on repeating them. However, the consensus was that this is not a good idea. So in the GPT-3 paper, they write data are sampled without replacement during training. And then 2 years later in POEM from 2022, they say that we train all 3 models on exactly 1 epoch of the data and choose the mixing proportions to avoid repeating data in any subcomponent. And so prior work was very against the idea of repeating. However, it wasn't really clear why, since as you all know, in many other areas of machine learning, it's very common to repeat the data and train for multiple epochs. However, for those large language models, it was considered harmful. And so the first question we ask really is it really that bad? And can we quantify how bad repeating data really is? All right, so to answer that question, we have a bunch of configurations. So we have 3 core configurations that we focus on, which are pretty large because, again, this question only matters for large language models. So we have to go through those a bit larger scales. So we have those 3 configurations. The first one, 2.8 billion parameters and 55 billion tokens. The second one, 4.2 billion parameters and 84 billion tokens. And then the third one with up to 8.7 billion parameters. And the way we chose those is we took those 3 training compute budgets And then we just use the equations from the chinchilla work that we briefly covered before. And we can directly compute the optimal number of parameters and tokens. So these are all just optimal configurations given the flops. So for 9.3 E20, the optimal configuration is 2.8 billion parameters and 55 billion tokens, and so on. And we just choose those optimal configurations to make sure we get the best models possible. And then for each of those setups, we train 8 models with different amounts of unique training data that is repeated for different number of times. So for the first one, we have a base model that has those 55 billion tokens that are entirely unique. And then we have a second model that has 28 billion unique tokens that are repeated twice. And then another one where it only has a third of those tokens, and they have to be repeated 3 times to reach the full 55 billion tokens, and so on. And in addition to those 3 core configurations, we run roughly 300 more models that are different in terms of their training data and different in terms of the model size and training data for some additional ablations. And across all runs, we use very common presets in order not to have any confounders in the presets. So we use the architecture from GPT-2/GPT-3. They use the same architecture. The hyperparameters come from Chinchilla, and the data sets are pretty common web crawls like C4, Oscar, and so on. All right, so let's look at the value of repeating data. So here we have these 3 configurations that we just covered, 2.8 billion parameters, 4.2, and 8.7. And then on the y-axis, we're measuring the validation loss, which is our performance proxy. So the lower, the better. And on the x-axis, we have the number of training tokens. So that's kind of the training progress as we train those models. And so for the first model where the entire training data is unique, these are the loss curves. And as expected, the 8.7 billion parameter model finishes with the best loss simply because it has much more compute, but nothing special here. This is just entirely unique data, like it would be common for large language models. And then we start repeating. So this is 2 epochs, which means that only half of the training data is unique. So for 55 billion tokens, 28 billion would be unique for the first setup, and then they have to be repeated twice. And for the second one, for the 2 epoch line, 42 billion tokens are unique, and they're repeated twice. And surprisingly, they kind of overlap. The lines are pretty similar, so we're not really seeing any performance degradation from doing 2 epochs, so only having half of the unique data available. And this is quite important because it means essentially you can just take half of your training data of current large language models, and then you just repeat it twice, and you get roughly the same benefit as having had, the entire corpus as unique data in the first place. And so then we do 3 epochs. So now just a third of the training tokens are unique. And 4, 5, 7, 14. And now we do start to see some performance penalty. So the 14 line is quite separated from the others. So we do see that eventually, you can't just repeat forever, which makes intuitive sense. And then for 44 epochs, it even starts to diverge completely. So in this setup, we have for the first one, for the 55 billion tokens configuration, we only have 1.3 billion unique tokens, and they are repeated 44 times in order to reach the full 55 billion tokens. So that's really not a lot of unique data, and it kind of makes sense that it should be pretty bad. And in fact, it even diverges. However, for those few repetitions, we get roughly the same performance, very similar. And so there does seem to be some value in repeating a couple of times. So let's try to quantify that value. So we hypothesized that you can model repeated data, or the value of repeated data as exponential decay. And intuitively, each time that you repeat a set of unique data, it loses some fraction delta of its prior value. So at each time sort of you repeat it, it decays a bit in its value. And I think intuitively that makes a lot of sense. Like you only, at each point, some fraction of the value of that repeated data, because you have already seen it, it is gone. And eventually, there's no value left because, at some point you've seen it so many times, you can't get any value out of it anymore. And this is very similar to many other phenomena in nature, like radioactive decay, for example, is exponential. So you start with like 10 grams, and then it halves to 5 grams, 2.5, 1.25, and so on. And so in this case, it halves every time, but it could also be a decay where, it becomes even less. It becomes a quarter every time, or it stays the same, so no decay, or full decay where it just becomes 0 after the first iteration. Right. So now, all we have to do is, assuming this exponential decay model, all we have to do is just sum up the value at each repetition. So here we have d prime, which represents the total value of our data, and then u is the unique data available, and rd is the number of repetitions that we repeat the unique data for. And so at the first repetition, it's just the value is just u. It hasn't lost any of its value. And then the second time we see the unique data, it loses some fraction 1 minus delta of its value, and then 1 minus delta squared, and so on until we reach the number of repetitions. And so if delta is 1, then this corresponds to the base case where repeated data is worth nothing. So all the other u's, they just fall away, and we only get value out of it at the first point in time. Everything else just becomes 0. And inversely, if delta is 0, then it is as if repeated data is just as good as new data. So all the other, so 1 minus 0 is just 1. So all the other u's just stay, and it's just u plus u plus u plus u until we reach the number of repetitions. But both of these scenarios are quite unlikely given the graphs that we saw earlier. So it's probably somewhere in between. And for example, if it's 0.5, yeah, go ahead.
Yeah, sir. A quick question. So like this is first of all, this is like the hypothesis you want to test, right? Like just to sure. And but how does it model the part where like it goes back up? It's like basically in this case, like the extreme case is that it doesn't add any value, but like does it model like that it hurts?
Yeah, it doesn't
repeat.
It doesn't.
Okay.
Yeah. We'll go into that later actually, but yeah, as you say correctly, so it only decays to 0, and we don't let it decay into negative territory.
Okay, so it's not like taking into account the kind of the potential optimization problem where it could hurt.
Yeah, exactly. It doesn't consider that.
Okay, cool.
And yeah, actually, yeah, go ahead.
Sorry, do you have any sense of how sensitive this is to the optimization procedure, like learning rates and algorithms and things like that?
So we do some we change the training data. So we do ablations depending on the training data. We don't do ablations with the hyperparameters, so the learning rate, for example. But yeah, I imagine that it could change. So I think one thing that could change a lot, could change the curves a lot, is regularization. So for example, if you just early stop, so obviously in those graphs earlier, we didn't early stop, but you could just early stop as soon as it diverges, and then that changes it quite a bit. Yeah, but for most hyperparameters, we just use the values from Chinchilla, so it's pretty common hyperparameters. But I do imagine that there's some effect depending on those. Yeah. Does that make sense?
Yeah, and do you think, I mean, it seems like from the findings so far that you should be training over multiple passes of the data set. And I wonder if that means the models that are deemed optimal by Chinchilla results is actually under-parameterized, because it seems like you can do multiple passes with the model and still get results, which means that the ones that are underfitting, maybe if you increase the model size, that could help with the problem.
I'm saying if you should increase the model size for the chinchilla models.
Yeah, so because I think the chinchilla results are under the assumption that you do one pass on the data, right?
Yeah, exactly.
Right. So if the assumption is that you can do multiple passes of the data, now there's another dimension to that whole chinchilla optimal models, and the results that you know the current optimal hyperparameters might not hold if you allow it to be multiple passes. Does that make sense?
So like I didn't quite catch it. So the hyperparameters, you think the hyperparameters in chinchilla they're not optimal, or?
Well, if you add another dimension to the space, which is the number of passes you can do over the data set.
Yeah, okay, yeah. Well, I think let me try to answer that. Let me know if it's not the right answer. But I think the so if you don't have, if you have unique data, then it doesn't, like, repeating doesn't make any sense. Like, you should just use as much unique data as you have. But yeah, if you add this third dimension of doing multiple passes, and you are data constrained, so you don't have enough data available according to chinchilla, then you should repeat it. Does that make sense?
Right. Yeah.
Like, otherwise you want to stay in chinchilla. Like, if you have enough data, then just stay within what chinchilla suggests if you want to train a compute optimal model. And otherwise, if you don't, just repeat. Yeah.
I'm saying there could be a new chinchilla study where there's an additional dimension of like how many passes you do over the data set. Maybe, you know, using the results that you have here, maybe. But that's another discussion.
I mean, I guess the point sort of is I mean that won't be that won't be compute limited anymore. Right? Like if you train for the same data twice, the compute would go up.
Yes.
But we're saying that would maybe be strictly better. Because I think the chinchilla thing is kind of constrained by compute.
Yeah.
Yeah. So here it's like we're adding another constraint, which is data, right? So we have the compute constraint plus a data constraint. And the chinchilla kind of assumes there's no data constraint. And if there's no data constraint, then this work doesn't really matter. Like, you don't want to repeat.
Yeah.
Thing. We have some, so later on we have some we make some changes to the chinchilla equations and show how we can incorporate these results with chinchilla. Maybe that answers the question better.
Okay. Yeah, for sure. Thanks.
Yeah, cool. Thanks for the question. All right. Anything else? Okay, cool. Yeah, so we have this term where we sum up the value at each repetition. And then in order to make this term a bit simpler, we approximate it with this approximation. And it just comes down to removing the delta and instead introducing this parameter RD star. And this makes it a bit easier to interpret because RD star corresponds to the number of times you can repeat before you see sharply diminishing returns. So we can directly interpret RD star as telling us how many times to repeat at max. If we repeat more than that, we're gonna hit really sharply diminishing returns. So if RD star is 0, then the second part just becomes 0 and we're just left with U. So that's, again, as if repeated data is worth nothing. And if it's infinity, then it's as if repeated data is just as good as new data. Cool. And so now we get back to chinchilla.
Sorry.
Yeah, go ahead.
Nicholas.
Yeah.
Then make sure my understanding is correct. So if the delta is 0.5, means that you in the second epoch, so if you train on the same data, you get like 50% new data. It's equivalent to having a 50% new data. Is that correct?
So for the first equation, yeah. So if you, yeah, exactly. Yeah, that's correct. So it's like as if you had done.
Yeah.
Yeah.
So, but the model size you computed based on the scaling rule is you have the assumption that you only train the data for one epoch. So
Yeah.
if you train data for more epochs, you probably need a larger model according to the scaling rule.
So we don't know. So that's what we're trying to answer, and we'll try to answer this in a bit.
Okay.
And we'll actually show exactly how you should do it. But yeah, at this point we don't really know,
Okay.
so we just use those same configurations. Yeah. Okay, cool.
Thank-
Yeah, so let's get back to chinchilla. So this was the chinchilla equation to estimate loss given the number of parameters and the data budget that you have, or the amount of data that you have, D. And so now we just use this term that we just discussed, and we replace D with this term. So this sort of corresponds to our value estimate of the data. And then we do the same for N. So we have a symmetric version of this term to also replace N. And it's the exact same thing except for replacing D with N. And UN here, so the number of unique parameters, corresponds to the optimal number of parameters given the unique data budget. So we can just use the chinchilla equations to compute this N opt. And this is sort of the number of parameters that give an optimal fit for UD. So in those configurations we saw earlier, for 55 billion tokens, if we have 55 billion tokens of unique data, then UN is just 2.8 billion. So the corresponding optimal number of parameters. And yeah, it's the min of that or the actual number of parameters if they're lower. So it's like UN is the optimal fit, and then Rn star is sort of the number of times that we can repeat those unique parameters before we see sharply diminishing returns in adding excess parameters. So it's like we also decay the value of excess parameters, essentially. And we use roughly 200 training runs to fit RD star and Rn star, and we get these values. So RD star is roughly 15.4 for our training data, and Rn star is 5.3. So 15.4, again, we can directly interpret this as telling us you can do roughly 15.4 repeats before you start seeing sharply diminishing returns. And this corresponds to a delta of 0.06. Yeah, and then for Rn star, it's 5.3. So you can have roughly 5.3 times more than the optimal number of parameters for your unique data before you start seeing sharply diminishing returns in adding excess parameters. And what's interesting here is that Rn star is lower than RD star. So this tells us that adding excess parameters decays faster than excess repetitions, than repeating data.
Wait, sorry, Nicholas.
Yeah.
I didn't quite the repeat, like extra parameter part. Like, what do you mean by adding extra parameter?
Yeah, so it's like, yeah. Maybe that's unclear. So it's like if we have a certain unique data budget, so let's say we have 55 billion tokens, and then the corresponding number of optimal parameters is 2.8 billion. So this would be the value for UN if we have 55 billion unique tokens. This is N opt. And that just corresponds to sort of the number of parameters that give an optimal fit for UD. And if you're N, so your actual number of parameters, right? So you have 55 billion tokens, but you're training with 10 billion parameters, so much more than optimal, then Rn star would be those 10 billion divided by UN. So 10 billion divided by 2.8. So sort of you have 4 times excess parameters, if that makes sense. And then Rn star just determines how fast those excess parameters decay in value. The reason we do that, I think intuitively it makes sense, because if you have more parameters than optimal, then they should also decay in value in some way or another. And since we're just using data to estimate Rn star and RD star, if the data tells us that this is wrong and excess parameters should not decay in value, then Rn star would just be infinity, and then this is just the same as N. So this formula really, it's just an extension of chinchilla. You can just plug it in for chinchilla, and it also works for all other cases of chinchilla. It just will change once you're hitting that regime of having multiple repetitions over your data, or having excess number of parameters together with an Rn star that's not infinity. Did that help? Does that make sense?
Yes. Thanks. I think that makes it clear.
Yeah.
Wait, I have another question. So, like,
yeah, go ahead.
If you want to predict the loss of like a certain model and a certain like data budget with like a certain type of repetition, it's like n dash now the actual model parameters do you have, or is the like original n like in this sort of UN the model parameters that you start?
Yeah, the actual model parameters is just n. So
Okay.
the actual parameters of the model we train, and if it's more than n opt, so if it's more than the optimal number of parameters, then Rn star will reflect this factor, just like Rd star reflects the number of repetitions. Rn will reflect the number of access parameters. Does that make sense?
Okay, so sort of like the effective number of parameters that you actually.
Again,
My question kind of how to interpret the n dash. Is it like kind of the effective number of
the n prime.
parameters?
Yeah, so that's the n prime is just the sort of the estimate for the value of parameters. It's not the actual number of parameters. It's the estimate for the value if we were just training in the usual chinchilla setup. Maybe that helps. So and d prime the same. So d prime is the estimate for the value of our data if we were just in the usual non-repeating data setup. And if we're not repeating, then d prime is the same as d, right? If we're not repeating, then ud is the same as d prime is the same as d, because we don't have anything here. This is if the RD is 0, then all of this just becomes 0.
Thank you.
All right, cool. Yeah, we'll look at some visuals now. So I think that will help drive this home.
I also have a question.
Yeah.
So Nicholas, so this equation, like no matter if it is the original original scaling law, or the adapted scaling law, I don't like for all the experiments that you run to fit the parameters of this equation, like it has to be the runs that don't overfit, right? These equations don't really capture overfitting behaviors.
Yeah.
Is that correct? Okay.
Yeah, that's a great point. Yes, since we're not decaying into negative territory, we're only selecting the runs that are not overfitting and diverging. Yeah.
Okay. Is that the same with the Chinchilla paper, right? I guess like for all the scaling law parametric fit to these equations, I guess they have to make sure that the runs are not overfitting. Otherwise, it's like does not really hold it, right? Like in a case where like you have a fixed amount of data and then you just keep increasing the model size, and then clearly it will overfit as you increase the model size to some point, and then that data point would not fit this law, I guess.
Yeah, exactly. I think they don't even train such extreme models. Like obviously they don't repeat, but I also don't think they have like huge number of parameters with very little data. But we have a bunch of those. And we'll see.
Yeah, I see those
Yeah.
points in the paper. All right, thank you.
Okay, cool. Yeah, thanks for the great questions.
Sorry, I have
okay. Yeah, go ahead.
yeah. So are this
Go ahead.
conclusions specific to a concrete size of model? Like when you get the R star, you run on I think a specific model, and how large is that? And can the conclusion generalize to different size of model?
So in those 200 training runs that we use to learn RD star and Rn star, there's a bunch of different scales. So there's some models with like 80 million parameters and some models with 9 billion. So it's
all, like,
yeah.
I see it. So the all the R star you got are similar.
Yeah.
Different
So
models.
we fit all of them in one, and then we get this value. So it should generalize. So it generalizes across all of those different values. And in fact, we'll look at those. We'll look at a bunch of different scales in one of the next plots and see how it seems to apply to different scales.
Okay.
Yeah, but I think it's universally applicable regardless of the scale, more or less. And you don't know a trillion parameters, but yeah.
Okay, one last question, Niklas. Thank you for your explanations. I think this is really fascinating, right? Because like the actual like sort of plot budget should be like UD UN times 1 plus RD, I guess. So you're kind of like the data part of that diminishes as you repeat, but like this n dash, this like extra kind of model capacity which you gain in the chinchilla formula would not be, I mean, you kind of save on those flops because you don't actually like compute them, right? Like your model is actually smaller than these like excess model parameters. So does that mean like for compute efficiency, you would want to repeat?
No, I think for compute efficiency, you never want to repeat. Like if you, like assuming that you have infinite data available, you never want to repeat. But if you have, if you're data constrained, then you do want to repeat quite a lot. And we can show you like how to do it compute efficiently. I don't know, does that answer the question?
I guess, yeah.
You mentioned something about yeah, go ahead. Sorry.
Don't follow up to that. If I had infinite, I'm just trying to figure out how to read this. If I have infinite compute, but I have limited data, how would I read off this to determine kind of my model parameter budget?
Yeah, if you have infinite compute and limited data, then you will not be able to make use of that infinite compute because there will be a point where you hit diminishing returns and you can't get any more out of your data. But you can do a certain number of repetitions and make use of a lot of that compute, but you won't be able to use infinite compute. Yeah, so your returns will just diminish, and we'll see this in one of the next plots. But you won't be able to make use of that full compute. Does that make sense?
But I can project the compute that I should use from this equation, right? This is the n. This is the n prime.
Yeah, exactly. Yeah, we can. We have some equations where you can directly predict, given your amount of compute, how much parameters and how much repetitions should you do. Yeah.
Okay.
Very cool. Maybe the next slides clear up some more questions, but feel free to jump in if there's anything else. All right. So now let's try to put the function to use and predict loss. So we fitted the function on all of those training runs, and now we'll use it to predict. And so here on the left side, we have the final test loss on the y-axis again. So this is our performance proxy. And then on the x-axis is the fraction of training tokens that are unique. So at 100%, it's just the base case where everything is unique. And then 50%, half of it is unique and it has to be repeated twice, and 25% and so on. And yeah, let's add the first configuration. So this is the 2.8 billion parameter configuration that we saw earlier. And here each dot corresponds to one empirical model trained. And then the solid line is the loss as predicted by the formula. And the diagonal kind of dashed line above is the loss that we would expect if repeated data would be worth nothing. So this is if, RD star is 0, if there's no value in repeating data, or delta if it just decays by 100% after the first repetition. And then the dotted line is the hypothetical value of repeated data if it would be worth just as much as new data. So the opposite. And as expected, we're somewhere in between. So we're not getting the full value, like it's not as much worth as much as new data, but it's also not worth nothing. And yeah, the line and the dots actually align fairly well. All right, let's add the other configurations. So 4.2. And of course, the final test loss is lower because we have more compute for this configuration. And then the third one, 8.7 billion parameters for 178 billion tokens. And it does seem like the fit is slightly better for the largest model. So maybe there's less randomness as we have more compute allocated to it, and we get a slightly better alignment of the line and the dots. All right, and so now on the right side, let's change the training length and predict how loss would behave for trillions of tokens. So for the first setup, the solid line here corresponds to the predicted loss by the formula, And then the dotted line again is the loss that we would expect if we would have lots of unique data available, like infinite unique data. And we see that, you know, as we keep repeating data for multiple epochs, it starts to flatten out. So this is this kind of decay in value. And at roughly 64 epochs, we're not getting anything out of it anymore. So it doesn't make any sense to repeat at that point in time. And then the second and third configuration, so they all just flatten out. So this just tells us, yeah, what's the value that we get as we progress through training and we train for more and more tokens. And for roughly 4 epochs, we're having that, like, the two lines are pretty much on top of each other, very close to each other. So we're getting yeah, almost the full value out of repeated data. It's almost worth as much as new data. But then eventually, you know, the lines start to diverge. And in fact, roughly around 16 epochs, we start to see really sharply diminishing returns. And this is because the RD star value that we fitted is 15.4. So it's right around there. And that's where, you know, it just starts to completely flatten out. All right. So now this was the value of repeated data. And now let's look at the allocation. So maybe this, so this comes back to Chinchilla really. So a quick reminder for Chinchilla, which is, as mentioned before, assumes you're not repeating data. The allocation is equal. So you equally scale up model size and training data as you increase the flops. But how does it look like when we're repeating data? So for to answer this, we train a bunch of models on 100 million tokens of unique data, and then we change the model size, the number of parameters, and the number of times that we repeat those 100 million tokens. And here's a plot of those models. So each dot corresponds to one model, and then on the y-axis we have the number of parameters, and on the x-axis the epochs over those 100 million tokens. And the color of each dot and the contours correspond to the loss. And again, the starting point is just one epoch, so no repetitions. And the corresponding compute optimal model has 7 million parameters. So that's sort of the baseline. If we're not repeating data and we want to train a compute optimal model. And for that, the loss is 8.1. But then as we add more and more parameters and we add more and more epochs, we get better and better loss. So it's, you know, if that is the data you have, you definitely want to go beyond that. You want to repeat. And in fact, we get more than a 50% reduction in loss at like 59 epochs and 146 million parameters. And so that's the white star. And then we see, so this is what we alluded to earlier. Then we see that the loss beyond that, it kind of increases again. So this is where you're in this hardcore overfitting regime. And yeah, and kind of the contours start to become full circles. And so this is all empirical on the left-hand side, but now let's predict those same contours with our formula. And so this is how the formula would predict those contours. And so the big difference, of course, is that it does not allow for negative value in repetitions. So instead of circles like on the left-hand side, we just have curves. And yeah, and repeated data can never have negative value, or access parameters can also never have negative value. So eventually, you know, it just decays to 0. It doesn't decay into negative territory. But other than that, the contours look quite similar. And for both contours, you see that the kind of the distance between those lines increases as we move to the upper right. And these are the diminishing returns that we get. So as we repeat data, it loses more and more of its value. And so eventually, you know, doing one additional repeat doesn't have a lot of value, and we're seeing stark diminishing returns. And you have to really go a lot further to get better loss.
So I think this question.
Yeah, go ahead.
Yeah, so earlier we saw the curve where when the epoch increases, the loss starts increasing and diverging. But on the left-hand graph here, for example, for parameters like 70 million and 146 million, it seems like when you increase epochs from like 30 to 1000, the loss never diverges or increase. Do you have like some like reason behind why this like in this case the loss doesn't diverge?
Yeah, that's a good point. I think so this is here we're measuring the final test loss, while earlier it was the loss throughout training where it started to diverge. So that could explain part of the difference, but then also I think the one part of the difference is the scale. So I think that at smaller number of parameters, you don't see that much of an effect that this kind of I don't think you have the same kind of diverging happening. So if you go up a bit, then you see that it seems to become a bit more apparent. So if we look at, for example, let's say the 709 million line, then the contour is clearly close, right? Like you just clearly see worse loss. Like the points start out being again like orange and then they become black. So I think it has some relation to the scale of the model, and then also that it's just the final test loss here and not throughout training.
I see. Thank you.
Yeah, and I think it also I think these plots also answer the question we saw earlier. So if you that you mentioned earlier, if you have infinite compute but limited data, you won't be able to make use of that infinite compute because eventually there's just nothing you can get out of your data anymore. Eventually you've repeated that many times that you're at this white star, and even though we go beyond, we train a bunch of models with like many billions of parameters even on these 100 million tokens, which is really not a lot. We don't get any additional value out of it. So this is also the extreme models that we referred to earlier. So we have some pretty extreme models here with like I think 8 billion parameters and 100 epochs over just 100 million tokens. So I think in Chinchilla and in most prior work, they didn't go into such extreme configurations. And yeah, it hurts. Performance isn't very good for those. All right, and now let's add in the efficient frontiers. So the Chinchilla work again suggested that you should equally scale parameters and training data. And so the black dashed line assumes that like if we were to assume that also holds for repeated data, this is how you should scale up. Starting from this compute optimal model at 7 million parameters and 1 epoch, this is how you should scale up your compute. So equally scale up parameters and epochs or training data. However, if we account for the fact that we're repeating data and we use our equations to predict the efficient frontier instead, then we get this line on the right-hand side that drifts off below the equal scaling line. And eventually it vanishes because there's no value you can get out of repeating anymore. And the reason it branches off below is again earlier because of the parameters that we fit it. So RD star was bigger than RN star, which means that the value of excess parameters decays faster than the value of additional repetitions. And so that's why it branches off below. If both of them would be equal, so if RD star and RN star would be equal, then it would just overlap with the dashed line. And in fact, you see it overlapping before 1 epoch. So before we enter the repeating regime, they just overlap. And that's because our formula is exactly the same as Chinchilla in that case. It just reduces to Chinchilla.
One question.
Yeah, go ahead.
Do you think RD would ever be equal to RN, R star N, or even smaller, like given different architecture, or there should be some theoretical bound for that?
Yeah, I think that's an interesting question. I could imagine that maybe there's some better architecture where they would be equal. or even Rn star would be even bigger. One interesting direction would also be how does it behave with mixture of experts. So you have to be careful how you count parameters in that case, but maybe it looks different for that. Yeah. So we're only considering transformers here, just decoder transformers like GPT-2, GPT-3. But I imagine it could be different for different architectures.
Cool. Thanks.
Thanks. All right, cool. So this was pretty small scale. So this was just 100 million unique tokens. And then we vary the parameters and the epochs. But now let's test this hypothesis of scaling data faster than parameters at scale. So we train 2 models at larger scales. Here on the y-axis, we have the number of parameters. And on the x-axis, we have the number of tokens trained for and the epochs below. So we, again, have those 2 curves. The black one is the equal scaling, if we assume that we want to scale equally according to chinchilla, and then our data constrained efficient frontier that branches off below. And so if we train a model that lies directly on the chinchilla line with 10 to the power of 22 flops, so that's our compute budget, we get this loss, 2.376. So that model has 8.7 billion parameters, and then it is trained for 178 billion tokens, corresponding to 7.1 epochs. So that's the chinchilla model. And then if we train one model that lies directly on our efficient frontier, that we just investigated at smaller scales, but now at larger scales, we get the model with 6.34 billion parameters trained for much longer, 242 billion tokens. However, on the same amount of unique data. And that one has better loss, so 2.359. And actually at those scales, it might seem like a tiny loss difference, but at those scales, it is quite significant because eventually loss just decreases pretty slowly. So we do see a performance gain from scaling data faster than parameters in this regime. Yeah, both models have the same number of flops, same number of unique tokens. We're just changing the allocation to parameters and repetitions. All right, cool. So this was repeating. We looked at what's the value of repeating data and how should we allocate compute when we're repeating. And now we'll look at 2 more complementary strategies. We've got filling with code. So imagine that you have your data budget, and instead of repeating, you just fill up the missing data with code from those several trillions of tokens on GitHub that we discussed. And another strategy could be changing filtering strategies. So it's pretty common for those large-scale pre-training data sets to apply some strict filtering in the form of deduplication or perplexity filtering. And that can severely limit the amount of data available. So it might make sense to do a bit less strict filtering. All right, and so now let's investigate the performance of those strategies. So here we have, on the y-axis, we have the average performance on 19 natural language tasks, and we just average them all. And these are pretty common tasks like story close, Winograd schemas, COPA, and so on. And then on the x-axis is our data budget. So at 100%, we're good. We're not data constrained. We don't need to do any filling with code or repeating. But then at 50%, we have to repeat twice or fill with 50% of code, and so on. And each dot in this plot corresponds to one model. So we train a total of 97 models, and they all have the same compute. So each model has 4.2 billion parameters and 84 billion training tokens. So the compute allocated to each model is exactly the same. And for the red and purple lines, we additionally train 5 seeds and visualize the standard deviation. And what we're seeing is, so first of all, let's go back to repeating data. So previously we just looked at how it affects perplexity or loss, but now we're looking at downstream performance, and it validates what we saw earlier. As we move to the right, on the purple line, we're not seeing any penalty in performance. So even at 25%, which corresponds to the 4 repetitions, so we have 25% of the data and we have to repeat it 4 times. It even moves up a bit, but it's within the standard deviation. So just no performance penalty really. But then eventually at the end, it starts to drop sharply. If we're repeating a lot, it does hurt performance. And then the red line corresponds to filling missing data with Python code. So this is code from GitHub, only Python code. And what we're seeing is that it kind of follows the purple line for quite a bit, which is quite interesting since that the tasks we are benchmarking here are entirely natural language. So there's no coding tasks or something, but it seems like there's no penalty, even though we're filling with like 50%, 60% of code. Eventually it does start to drop, and training on code only is not going to give you good natural language task performance. And then we have those 2 stars, which correspond to filtering strategies. So for perplexity filtering, it does seem like it helps quite a bit. However, if we deduplicate, it doesn't really seem to help a lot in this case. And let me just put these in. So the reason the duplication might not help here is because the data sets we are training on have already been sort of fuzzily deduplicated. So we're training on C4, which is a web crawl, and they already have some filters applied to it. And so if we deduplicate it again, if we apply another set of filters, it seems like it hurts performance. And it just constrains data and doesn't really help in terms of performance. And when I talk about deduplication, it refers to, in this case, we're referring to selecting a certain, so you select a certain, or you check for substrings that are repeated in the data. So it's not like we're only removing samples that are exactly the same as others, but we're selecting a certain substring length. And then anytime the substring is repeated in the data, those repetitions are discarded. So for example, we're selecting a 200 characters, a 200 character substring, and whenever this one appears again in the data, then that repetition gets removed. And again, this doesn't seem to help performance. So this is how deduplication is done for most data sets. You just change the substring length depending on how strict you want to deduplicate. Yeah, so the takeaway from this slide is really repeating is good. You can also fill with code, and be careful with too much deduplication.
One more question about the data.
Yeah.
So is it like randomly shuffled, or it's like you train on the unique data first and then the code data?
It's randomly shuffled.
Oh, okay. That makes sense.
Yeah. And also for the repetitions, at the beginning of each epoch, we also shuffle the data. Yeah. And it's maybe an additional point here is that the code is made such that there's maximum overlap. So if we are training for 50% of code, if we have 50% of code in the data, so there's some red dot in the middle, then those 50% code are also included in all the dots towards the right. So it's always the same kind of, it comes from the same pool of Python code. That makes sense.
Makes sense. If you evaluated this on like perplexity or like on other validation does, or like the kind of natural C4 data, would code still help, or presumably it would do worse?
It would do worse. Yeah. If we instead measure perplexity, then code would do worse. However, if you measure perplexity on code data, of course, it would be better. Yeah. So it's questionable. Like that's why we're choosing natural language tasks here, because that's what we care about ultimately. And perplexity would be a bit confounding in this case. Also for the deduplication and perplexity filtering ablations, it's unclear whether if you're measuring loss, do you want to measure this validation loss on also a deduplicated validation set or not, or also a perplexity filtered data set or not?
Yeah, makes sense.
And in fact, the loss graphs are also in the appendix of the paper. So there's some loss graphs for each of those runs too. Okay, cool. Yeah, so with that, we'll wrap up. So in the beginning, we talked about scaling and why it's critical for progress, but faces data constraints. And then we looked at the first remedy for solving those data constraints, which was repeating. And really the two takeaways from repeating were that up to 4 to 8 times is pretty good. For 4 times you get roughly no penalty in performance. However, there are diminishing returns, and we can predict them with an exponential decay formulation. And secondly, if we're in this repeated regime, then we'd like to scale compute allocated to data faster than the number of parameters. And then in the end, we looked at complementary strategies. So these can be combined with repeating or used as standalone strategies. And we saw that adding code gives us roughly another 2x without any penalty in terms of natural language performance. And we should be careful with excessive deduplication. It can save us orders of magnitude of data. If we're deduplicating too much, we might be losing that data. And I think that's it. Thanks a lot.